Next up is Martino Plebani, who will present joint work with Carrara and Enrico Martino, on computability, finiteness, and the standard model of arithmetic.
Well, for a paper with 3 co-authors, there's just one half of them awake here now. So that no, one half of one of the 3, so 1/6 of them. Yeah, it's basic mathematics. I think I can. Anyway, let's get to the plan. In this talk, we are going to address one question, that is the question of what fixes the model of arithmetics. The question, and we are going to just confront 2 answers to our question. One is an answer from Horsten in a 2012 paper, and it's an answer according to which we fix the model of arithmetics using the notion of computability. And then we are going to present our take, our different fix on this, in which we argue that it's via the notion of finiteness that we are able to isolate the standard model, the structure of which arithmetics is about. And as you can imagine, we are going to argue that our answer has some advantages over Horsten's one. And then I'm going to turn to some objection, just to leave no space to the discussion. And let's go. The question, to put it in Horsten terms, is this one. How do we manage to single out the structure of the natural numbers as the interpretation of our arithmetical vocabulary? So this is the question we are going to address. As you see, the point is about the structure, not a particular model. And it's important to understand the question in the right way. So it's a question about reference fixing, about what determines the reference of our arithmetical vocabulary. It is not a skeptical question, so it is not at stake here that we do refer to the standard, to a certain structure. And you can put it in various ways. I just say some what fixes the model, fixes the structure about which arithmetic is about, or in virtue of what does our arithmetical vocabulary refer to a certain structure. It's important that the question is how we do refer to this structure, not whether. So, to say it with Horsten, we are not going, we know, both I, Scholar, Carrara, Martino, Horsten, everybody knows that we could, with Scholar and Putnam, deny that arithmetic has an intended interpretation, but we are going to do the opposite, and we will, following Horsten, we will presume that we can isolate the natural number structure in our referential practice. As I said, I think 4 times, it's the question we are addressing is not a skeptical one. And to get an idea, when we try to have an account of how we do refer to individuals, for instance, suppose we put forward Kripke's account of how we refer to individuals, we are not trying to address skeptical queries about the existence of individuals. The same can be said when we are addressing the question about how we do refer to unobservables. It seems that it's a different question than the question whether there are any unobservables. So, now we can turn to the answer. And this is a very ad hominem talk, so let's start with Horsten's answer. According to his 2012 paper, but there's also previous work, and he's not the only one to go this way. The reference of our arithmetical vocabulary is determined by two factors. One are our principle of arithmetic and the use of an algorithm of computation. So there are these two ingredients. And of course, the reason why we need an extra ingredient over and above piano arithmetic, so which is what is doing the work of our principle of arithmetics here, is that we all know piano arithmetics admit no standard models, so it's not enough to fix the interpretation, it's not enough to fix the structure. According to Horsten, what does fix the structure behind PA is that the requirement, the constraint that the addition function must be computable in the models we are interested in. And to give a sketch of the reasoning by which we, using this notion of computation, we get to isolate the structure of arithmetics is about. Of course, by Church thesis, if the function is intuitively computable, it is Turing computable. And by Tenenbaum's theorems, all models of piano arithmetics in which the addition function is Turing computable are isomorphic to the natural number, to the standard model of arithmetics. So putting the two pieces together, we get that all models of piano arithmetics in which the addition function is computable are isomorphic to anything different than the set, of course. It's important, of course, to understand what notion of computation is in play here, and as Horsten himself stresses, the sense in which we are saying that addition is algorithmically computable is not to be understood in a formal way as Turing computability or Moore recursiveness. Here we are operating with the pre-theoretical practical sense of computability which has motivated the mathematical definition of computability. This is important because we are going to make use of another pre-theoretical notion, informal notion. So we are on a par with Horsten on this. Now you have all the basic elements to understand Horsten's answer. So the idea, as we say, is that there are two elements, the principle of arithmetic together with our use of an algorithm of computation. Now it's time to turn to our different fix. So our idea, the CPM thesis, is that Carrara, Martino, Plebani, is that we managed to single out the structure of natural numbers through the intuitive notion of finiteness, in virtue of which we can understand what the syntactical entities of the formal language of arithmetic are. So finiteness is going to do the job here instead of computability. What we have in mind here is that we understand what the structure of natural numbers are by understanding how to generate them. So that is that we start with just one stroke, and then we understand that we can generate the natural number by adding one stroke and another one, and going on like this finitely many times. Going on like this finitely many times. And of course, if you understand what the notion of, if you have a grasp of this notion of finiteness that is in play in this generation process, you can even add to piano arithmetics the extra requirement that every natural number has an extra axiom, that every natural number has only finitely many predecessors. So imagine having a non-standard quantifier to add an extra quantifier to be read. There are finitely many x such that, and you add this axiom that every natural number has only finitely many predecessors to piano arithmetics. Of course, in every admissible model of this extended theory is isomorphic to the standard model of arithmetic. Now, it's important to understand what finiteness in our framework is. It's not a sophisticated concept. It's not to be understood in set theoretical terms, nor it's a notion that has to be defined in second-order logic. And what it is, then, you could ask a question. And it is a pre-theoretical notion, just like Horsten computation. And as we were going to show, it is the basis to understand syntactical notions like numerals, proof, formulas, and as we will argue before, it is more basic than computation. So we have a friend of our side, we think at least, a very influential friend, so let's appeal to Hilbert authorities on this. Hilbert thought, I'm quoting, that a condition for the use of logical inferences and the performance of logical operation, something must be already given to our faculty of representation. Certain extra-logical, concrete, I would say quasi-concrete, but objects that are intuitively present as immediate experience prior to all thought. It must be possible to survey these objects completely in all their parts, and the fact that they occur, that they differ from one another, and that they follow each other or are concatenated is immediately given intuitively, together with the objects as something that neither can be reduced to anything else, nor require reduction. Is, I admit, a very long quote, but very important. So we have an intuition of surveyability and of discreteness, I would say, because the fact that you can concatenate these objects, Hilbert is thinking about finite sequences of strokes, it's because you can, because they are discrete, because they are finite, because of, and as Hilbert says, this is basic. This is the basic philosophical position that I consider requisite for mathematics and in general for all scientific thinking, understanding and communication. And in mathematics in particular, what we consider is the concrete sign themselves, whose shape, according to the conception we have adopted, is immediately clear and recognizable. What is important to stress here is that finiteness is a basic notion from a formalist point of view. So we are not talking about a notion that is important from a conceptual, Hilbert is a formalist. So let us stress that this notion was recognized as foundational, as basic, as very important even from a formalist perspective. Now, let us turn to how and why finiteness is more basic than computability. Well, if you look at the definition we give of entities like numerals, which are very important because are the things you compute with, they are finite strings of strokes, and formulas are finite strings of symbols meeting certain conditions, and proofs are certain finite strings of formula, and consistency is just when there is no proof of the absurdum. And so the definition of syntactic entities is based, it heavily relies on an understanding of the notion of finiteness, which means that any doubts about the determinacy, the intelligibility, the grasp of the notion of finiteness will backfire on, will result in a lack of determinacy of this other syntactical notion. There's also something to say about induction, but it's enough to stress the importance of finiteness for the definition of syntactical entities. Now, if you look at the two ingredients of Horsten and answer, we are going to show that they both, they both point to finiteness as a condition to understand them. So we're going to ask that both grasping what a syntactical object is requires an understanding of finiteness, and both grasping and also grasping the notion of computation presuppose and grasping the notion of finiteness. So, of course, PA is an object that is made out of syntactical objects. So PA is first of all a vocabulary, then a language, and in the language you have terms, formulas, proof, and so on. And we have just argued, remember, by the way, Field made the same point, so the quote refers to finiteness as the key to other two syntactical notion. But as we say, finiteness is the base to understand syntactical notion. PA is a syntactical object, so understanding of what PA is relies on understanding the notion of finiteness. But turning also to computation, it's part of the idea of a computation that it consists computation that terminates, that it consists of finitely many steps, and moreover, the primary object on which you perform a computation are finite sequences of signs, in particular numerals, that, as we argue, are defined in terms of finiteness. And also, if you also think about an important algorithm that is that of sum, the most intuitive grasp you can have of the procedure of addition is that you have strokes and you just concatenate them. And as you remember from Hilbert's quote, this concatenation presupposes that you're working with finite strings of strokes. Okay, that's our line. Let us just anticipate some possible objection. And we must distinguish between objection coming from the skeptical camps and objection coming from the computational structuralist camp. So one objection is the so-called just mode theory objection that says that as there are no standards model of piano arithmetics, there are no standards models of piano arithmetics plus the additional requirement that any natural number has finitely many predecessors. And you just have to give a non-standard interpretation of our quantifier, of a new quantifier. And of course that's right, but one obvious reply to this is that a completely analogous problem can be raised against Horsten proposal. So if any first order theory with an infinite domain has no standard models, also piano arithmetic plus some theory of computation and the requirement that the addition function is computable. So if the point is that you cannot isolate standard model, the structure of the standard model by using the resources of first order logic, we already know this, so it's no point to stress this. And you know, we know that the structure, the omega sequences cannot be defined in first order. To ask us to define them first order is just to ask. Would be like asking somebody who believes in invisible gases to show invisible gases. So of course we can meet this request. Neither Horsten can do, and we did say from the outset that skeptical doubts were not what we are going to address in this kind of account. But there's a more hard reply. I give a lot of importance to the soft reply, but let me mention a more strong reply. That is that we say that the notion of primitive, and it's what allows somebody to understand what an entity like piano arithmetic is, and only when you have grasped what an entity like piano arithmetic is, it makes sense to look for models, standard or non-standard of it. And moreover, as we say, if we lack a determinate notion of finiteness, we also lack a determinate notion of what syntactical objects, among them formal theories, among them PA are. So, to put it as a dilemma, either the skeptic has a determinate notion of what a theory like PA is, and if he does, if he has such a determinate notion, if he knows what the numerals are, then he grasps the structure of the natural number. He just has to look at his language to find what structure we are talking about. If no, then we need to be clear that there's a sense of vertigo here, because we not only know we don't only lack the determinate notion of what the intended model of piano arithmetics is, we also lack a determinate notion of what the theory is, of what numerals are, of what the proof, and so on and so forth. So I'm not going to say that this is an incoherent position, but it's a kind of global skepticism, and a very radical one. Of course, there's a distinction between the vocabulary of piano arithmetics, which is a finite list of signs, and the language of piano arithmetics, which includes the numerals, so a system of objects that exemplify the structure of the natural numbers, and we are just claiming that it's the language of PA that gives you an exemplification of the structure of natural numbers, not the vocabulary. Just to be clear. Now we can turn to the objection from computational structure. One objection is that in our account, if you take PA star, it's a theory that has only omega sequences as models, but of course in some omega sequences sum is not a computable function, and one could argue that if numbers are things we calculate with, then some omega sequences, those in which sum is not a computable function, are sequences where that do not contain the numbers, because we cannot compute with the elements of these omega sequences. But our reply is that we were interested in the structure of natural numbers, not in the natural number themselves. So we could even grant that natural numbers are things we count with, but this doesn't mean that the structure of natural number must be something we can count with. So, but moreover, there's a sense in which we have isolated the structure, because all the models of our expanded theory are isomorphic. So there is a sense in which they all display the same structure. If one wants more, if one, among the omega sequences, one wants to isolate the ones in which addition is computable, we have already argued that in any case, even in this case, the notion of finiteness must be grasped to do this, because the pretheoretical notion of computation, an implicit grasp of the pretheoretical notion of computation implies an implicit grasp of notion of finiteness. But there's another point that a suggestion similar to that we are pursuing here has been put forward to Horsten by Linevo. He says in the paper he considered a suggestion like the one we are advocating here, and the reply from Horsten is that mastery of the enumeration procedure, of the procedure to count numbers, is not sufficiently to single out the structure of the natural number. The problem seems to be that this does not guarantee that the domain of these could exhaust the standard natural numbers. And you could wonder why relying on the additional constraint that the addition function the computable should be different. And Horsten replies that it is part of the child elementary instruction to understand that the function is total. So the teacher that instructed the child says to him, in order to find the sum of any two natural number, this is the way you do. Okay, but it's not totally clear to me, but why our teacher could not say, in order to say something completely analogous, so in order to generate any natural numbers, this is the way you do. You add strokes a finite number of times, and this way you can reach every natural number. This is the way to generate them, there's nothing beyond that. So, just to review, we have addressed one question, we have confronted two answers to the question. The question is a reference fixing question. According to Horsten, we fix the reference of our arithmetical vocabulary via the notion of computability. According to me and Martino and Carrara, we do so by relying on our grasping of the notion of finiteness. We have argued that our answer has some advantages over Horsten, and that understanding of Horsten's notion of computation implies or relies on understanding our notion of finiteness, and that this notion is also needed to grasp the structure of numerals and of syntactical entities in general. Thank you.
Okay, so keep your hands up. So, Robert?
Just an historical remark, because you try to put Hilbert on your side, but be careful, because Hilbert says that the intuitive insight you have on strokes is not really what allows you to understand number theory. It says explicitly in the writings from the 20s, it says that there is the intuitive arithmetic, and then there is arithmetic that needs completeness, a consistency proof, but also a proof that allows you to bring the intuitive sides of the strokes, that presumably are not so many, to the insight in number theory. And also he said it in an answer to Husserl in 1901, it says, because Husserl was saying that he was able to give a complete description of number theory, and he says, are you sure you can do it with the language in the context of number theory? I guess you need something more. What he was thinking about more was logic, but in a very broad sense, that also allows a theory to be used to characterize them. So it's not so finitist as it could seem to be, Hilbert. So I'm not sure that it can help your position.
Well, the point of the quote from Hilbert is just that the grasping of the notion of finiteness is needed. So this is needed to grasp the structure of numerals. It doesn't mean that by this you get all the truth of arithmetic.
No, not even truth, but still it's not sufficient to have a clear picture of what numbers are.
Of what numerals are, you would say? Because they are identifying them.
Sorry, we have 10 minutes and 7 people in line. So Sam was next.
I thought your talk was really interesting, thank you. But I have a worry, and it's a worry that I think you mentioned as part of a reply to an objection, so we might actually just be at an impasse with each other. But so you say that PA star equals PA plus every natural number has only finitely many predecessors.
Yeah.
But it seems to me that maybe this notion of finiteness is too basic. Like maybe you're begging the question, because non-standard models are understood to be non-standard and worrying exactly in virtue of not having the property that every number has finitely many predecessors. And it might be that this applies to Horsten's account as well, if it's true that he relies on yours, but
yeah,
I mean, you still have to answer that.
That was my point. The software applies this. That if this is a problem, then also the notion of computation can have no standard interpretation, and then it has the same problem.
Yeah, but how does your account not suffer from that point? I mean, is your...
Well, I'm content in this content for the conditional claim that if there's a problem, if I have a problem with this, Horsten has a flaw. So it's a choice between which notion, which theoretical notion you should buy. Let's say, and I'm claiming that mine is more our is more good.
Okay.
One of the merits of your position against Horsten 1 is that finiteness is in some sense a more basic notion, and plus that in order to grasp the pre-theoretic notion of computation, you need some pre-theoretic notion of finiteness. Are you sure that it is does not hold also the contrary? Because I mean, for instance, in the kind of generation process that you describe, adding strokes, this kind of process, of course, embed a certain notion of computation. Also, on the other hand, more generally, I'm not sure that some hypothetical person that has no notion of computation can have at the same time any certain kind of notion of finiteness. It seems to me that the two notions are essentially very related. But while on one hand you got that the notion of computation fits very well in some formal counterpart under church thesis, you can't have any similar or any analog for the notion of finiteness.
Yeah, it could be that they are on a par, but just let me say one thing. Adding one stroke doesn't mean that you know how to compute arbitrary sums. You just know to go on in that procedure. So it seems something more simple in a way. And also that's the point of syntactical entities that seem more, the generation of syntactical entities seem to rely more on finiteness than computability.
Assuming, as you do, that you don't want to use second-order languages to characterize finiteness, it seems to me that one of a rather uncontroversial result of 20th century foundations of mathematics is the fact that a theory like P-A star can't exist as a formal theory. It doesn't exist, and it won't exist in the sense that it is unformalizable.
Yeah, it's unformalizable.
In principle, in a very strong sense. So this seems to me is rather a strong assumption. You use an in principle unformalizable. The problem is not the fact, of course, it must be an intuitive and irreducibly intuitive notion of finiteness. It's another way to see the same thing. But the point is that as soon as you try to put, to write down the basic principles about generation of numerals, etc., and then you go on. Well, there was a historical process that was not chance. I mean, it was not a sort of sudden passion for formalizing everything. No. First, we tried to put some principles, Dedekind, Grassmann, Dedekind, Peano, etc. Then you go to an axiomatization, then you go to a formal axiomatization, then you discover that you lose something in doing that. You gain a lot of things, but you lose something. And that's something that you lose. It's a sort of lost innocence. How can you take it back and say, no, okay, I'll do as nothing happened, and I keep my notion of finiteness. You can, but it is ineffable, in a very strong sense.
Well, ineffable means, it's like the point of show me invisible gases. As if ineffable means not first order definable, we knew it from the start. Yeah, I agree in this sense. But I try to motivate why it's so important. So if you want to say that we don't have a determinate grasp with this, okay, but then see how radical the position goes. I'm content to this. If you want to be skeptical on this, it's okay, but then you will be skeptical on the notion of computation as well. So.
Hi, I'm sympathetic to lots of things that you've said, but I'm not clear about the suggestion of grasping the notion of finiteness. Could you develop a bit what you have in mind? Usually, to grasp the concept is to have the ability to apply it in appropriate circumstances or to identify instances of that concept. Do you want to suggest that grasping the notion of finiteness involves being able to recognize instances of, say, finite strings of symbols or things like that? Or how should I think
I don't have a theory of how you display your grasping on this structure. What this is only part of the answer. It cannot be the whole of what it is. I don't have a particular theory. I'm just comparing costs and saying that if you want to doubt of this, you have to doubt of many other things, like that you have a grasping of what the numerals are. So if you are prepared to go for that, it's okay. But as I say,
no, I agree. May I?
Okay.
Okay.
That's very good.
Well, it was just that obviously there are finite strings of token symbols that we are unable to survey at a glance or with infinite amounts of time. Physical time. So in order to grasp what that string is, we might need computational abilities or a grasp of how these strings are generated. So I was thinking that maybe your emphasis on finiteness and grasp of finite strings might involve computational capacity.
yes. Good point.
So do you want
I think there is one fundamental difference between your account and mine. I think that hasn't perhaps come up very well. So it's you talk about grasping the notion of finiteness that is really required, and also grasping the notion of computation that is required for my account. But the account that I was trying to put forward may fail, but is that when the child learns to compute, then she doesn't have to grasp the concept of computation. That's not required. She only has to be able to compute. So give her any two numerals, she will apply the procedure and give you the results. And she doesn't have to know anything about finiteness or she does not have to have a general grasp of the notion of computation. So for me that was kind of essential, that the way in which actually the interpretation is fixed is in part by learning some theory. Say there is a first natural number, we call it 0, and every number has a successor, it's unique and so on. But also in part by practice, by just doing something without having to have the concept. So the concept of finiteness is not required, the concept of computation is not required.
Yeah, I didn't mean to say that somebody tells the children and you go on like this and you go on like this finitely many times, that one explicitly mentioned finiteness, but it is implicit in the way that the procedure of generating the numerals is explained. There's a way in which the pupil gets the way to generate that.
We have 1 minute left on Carlo. Do you have a super question? Fair enough. Well, there's two more. So Francesca.
It was already asked.
Okay. So here.
I think this is quick. I think I agree with everything you said. I think I agree with everything you said, but I must say that usually when I hear Leon or Volker or Paula talk, I end up agreeing with everything they said too. But I have a quick question for you. It's generally regarded as a major achievement of Frege's that he was able to define the ancestral of a relation. Do you regard that as somehow not an achievement because he could have just said, and it's an ancestral if there's a finite sequence, blah blah blah.
No, it's a great achievement, but it's done with upper level, higher level theoretical resources.
Oh yeah, no, I get that, but couldn't he have just, if he sort of, I can up myself to the notion of finiteness, then therefore I don't really need to define the ancestral. Or I can define it in a much simpler way.
I see. I don't think this makes Frege achievement less important, but I see I should be committed to say something like this. But the point is, maybe one point is that what I'm saying is that the implicit understanding of what finiteness is doesn't mean that you have explicitly formulated the concept. You just implicitly grasp which is the correct way to go on. And this means that you could have an implicit grasping of what the finiteness is and what amounts to, but you couldn't have defined the concept of finiteness. So this maybe Frege's achievement could have been to define what we implicitly were using all the time.
Okay, we're out of time, so let's time for